Welcome class, welcome to the lesson on vectors. Just an introduction to what we're going to be talking about today. Students will be given able to correctly diagram a complex vector. Students will be able to resolve vectors and be able to find a resultant vector after determining x and y components. Now the question is sometimes asked to me, when will I ever use vectors anyways? An interesting question. And the answer to that in physics is all of the time. You use vectors in many different units of high school physics. In kinematics, talking about velocity vectors. In dynamics, talking about force vectors. In electromagnetism, talking about electricity, electrical forces. If you progressed on to third level, you might learn about in modern physics about tensors. So it covers a wide range of topics. In the real world, so to speak, they're used to talk about things like air traffic controllers would refer to coordinates. For airplanes moving, traveling, for bridge construction, force vectors would come into play there, and even for football, American football, it would come into play in terms of lines run by receivers, and maybe a little bit, not saying that Tom Brady is going to be checking his vector coordinates when throwing the ball, but it does come into play in terms of giving instructions. So a very simple problem would be Long John Silver. He's trying to locate a little bit of treasure. Walked 15 meters east, then 30 meters north, then 15 meters west. What was his displacement? Well, this is a simple problem and is designated a simple problem. The reason is that there is all of these steps are in terms of x and y coordinates, they're along the axis, so they're 100% to the right or the north or the south or the left. Okay, so you can see originally he moved, the purple line is 15 meters east. So the initial one is 15 meters east, and this is important. So when we're doing this, the best thing that we should do, the first step should be to sketch the vectors. Okay, so sketch the vectors, and you're going to use a coordinate system for that. So the vector arrow, remember, the vector is designated with an arrow. And then we're going to join these up tip to tail like we learned last year. So the second one is all in the north direction. This is easy because there's no portion of that in the east or in the west. It's all going north, so it's all in the y direction. And the third one then is all west. Okay, so the third one is all west. Again, that's relatively straightforward because it's all going in the x coordinate. None of that is in the y. So we've joined them, we've sketched it, we've joined it tip to tail, and then we're going to break it into the x and y. So if we break it into the x and y, we can see that the purple and red line are both on the x. So we're going to take both of those. So we'll take 15 meters east and then minus 15 meters west. So in the x, it's going 10 meters. We always work off the coordinates. Generally in physics, we work off the coordinates that upwards and to the right is positive, just like the Cartesian coordinates. It just makes our life easier. We're used to that system, and it is necessary because the opposite directions are deemed and shown with a negative value. Okay, and then we look at the y portion. It is all in the positive y, so all of that is in the positive y. We don't need to take any away from each other. So it's gone 10 in the x, and you can show that just by going out here, and it's all in the y. And when we go tip to tail, you should see the broken dash shows the actual vector itself. Now, can we solve that using trigonometry? Sure we can. We've got a right angle triangle here, and we've got the various different, we've got the hypotenuse, we've got, depending on which angle, if you're using this angle here, we've got the opposite, and we've got the adjacent. So you can use the wonderful SOHCAHTOA to solve. It's important that you check for a reasonable answer. So if you need to solve that, remember you can find what the angle is here by using tan and opposite over adjacent, just like we did last year. In terms of trigonometry, you can just use Pythagoras' theorem to find the actual value of this line. So value by Pythagoras' theorem, angle by using trigonometry. Okay, so that's a pretty straightforward one. A more complex one would be something like this. You start at Boise, Idaho, and travel 563 miles at an angle of 41 degrees south of east to Topeka, Kansas. Then you go 620 miles to Albany, New York at an angle of 37 degrees north of east. Then you travel 653 miles to Montgomery, Alabama at an angle of 65 degrees south of west. Find the total displacement, magnitude, and direction from Boise to Montgomery. Okay, so looking at it on a map, I'll let you guys figure out where these wonderful places are. But if we look at the vectors, the pink vector represents the first motion. And this now you'll notice that they're two-dimensional. So there's a portion east, west, and north. So there's a bit in the x and a bit in the y direction. The first one is the pink one, second one is the yellow, and the third one is the purple. So my advice is always sketch it first, and you're going to sketch the three of those. And if you sketch the three of those, you'll see, roughly speaking, where the actual resultant vector should be. So if you look at this one, the resultant vector would be on my blue line, which would mean it would have a positive x and a negative y. So following this convention again, this xy convention, it will have a positive x and a negative y. And that will allow us to find, so we know, roughly speaking, ballparking it, where our resultant vector should be. Now, how do you solve these? Well, you break it up into the x and y component. So for each one of these turns, I'm going to break it up into x and y. So the first one we're going to look at is the pink one, which is going 563 at an angle of 41 degrees south of east. It means you start east and then you go south. So you're starting east and then you're going to go 41 degrees south. Okay. Now for that, we've gone 41 degrees south. We know that we can break this up. We break it into the x and y. So remember from last year, the x component, we multiply the overall velocity by cos of the angle, which is 41, and we get 424.9. If you want a little bit of a review on how you get that, well, it's basic trigonometry. So we'll get to that in a second. The equivalent for the y is 563, the total velocity, by the sine of the angle, which is 41. And we get that from the very top here. It's 41. Okay? And that's 41 degrees south of east. Sometimes there's two different ways to show it. So you can see both different methods on the board. Both mean the same thing. Now, why does that make sense that one is cos and one is sine? Let's look at the y value. So if we look at the y value, and we look at the theta, so this is an example of where it is. It is 41 degrees south of east. And if you look at that value, and you start looking at this in terms of trigonometry, this is the opposite side, this is the hypotenuse, and this is the adjacent. And so remembering that sine of theta is equal to opposite over hypotenuse, this SOHCAHTOA. And so if you rearrange that to get Vy, we want to get Vy now, it is Vt sine theta. Okay, because Vy is the opposite, and the hypotenuse is the actual V total, or the V that you're giving. So you're basically breaking it up into its x and y. Some of it is in the x direction, the blue line, and some of it is in the y direction, the red line. Okay, so we have both of those values. Now, there is a really important part here, and that is that it should have a negative y value. You can clearly see it when you draw it out, which shows you the value of sketching it, that it has a negative y value. It is underneath the y line. This is an area that students will fall down if you don't sketch it one after the other. One way that you can get around that is by using what's called the azimuth angles. So you're starting at this point that I've located here and working all the way around and taking the angle of the circle. Now we know that the full thing is 360, so the angle that I've just traveled there is 360 minus 41, which is 319. Now if you decide that you want to avoid all the sketching and all that, if you put in here 563 sine 319, it will actually spit out a negative value. So you don't need to change the sine value. So it will spit out a negative. If you simply use the original angle, which was 41, then you'll need to sketch it to know that the y should be negative. So two different ways to do it. One is by using the full angle starting from the blue line and working your way around to get 319. That will change the sign for you. The other way is just using the given angle and realizing from sketching whether it's a negative or a positive. Okay, the second one, if we work it out again, you're given 37 degrees and you're given 623. You simply cos for x and sine for y. However, we need to be careful. Always double check it, and this is why you might find that doing the azimuth is easier, because the question is it a negative or a positive? Now, the azimuth angle will help you in terms of whether it's a negative or a positive, but the question is the x component always a cos angle? And the answer to that is no, which is why I would recommend sketching it every time anyway. In this case, it turns out to be, but just by purely sketching it, you'll see which one is the adjacent angle, which is the cos, and that needs to be the x in order for that to be the same as on the board. Sketching basically is the best way to go. Sketching will also then show you whether this should be positive or negative. This is north of east, which means it goes east and then north. Travels east and north. They are both positive directions in the x, so it's a positive x and a positive y. And so you've got positive on both sides. Concept-wise, if you look at this one here, it goes south of west, which is to say you go west and then you're going to go south 61 degrees. Right, 61 degrees. Remember, you always start, when it's south of west, you start going west and then hit south. Or if you're using these coordinates here, it's the first one that you start at, which is the west. Now you can clearly see that this y value will be below the line, and the x value has also gone left, and so that will be a negative also. So when we say we use our references, those references would both be negative, left and down, because up and right is positive. Okay, so they will both be negative. So what do we do now? We add up the x components and the y components for each vector. So we have vector 1, vector 2, vector 3, and we've just broken them into the x component and the y component. Why do we do that? Well, we're trying to get an overall x value, and I've just sketched it here. But let's say this x value that we've come out with is 646.4. The y value that we've come out with is 622.4 meters per second. This is a negative. This x value is a positive. And we can see that the resultant vector will be to the right and down. So our overall resultant vector, which is this value here, when we move this resultant vector in, it should point to the right and down. Now if we go back to our original guesstimate as to where the vector would turn out, we can see here from this blue one that we said it would go to the right and down. So the last tip that I gave you as part of this in terms of stepping it through was check for a reasonable answer. make sure that it coincides, that it matches up to where you would expect it to be. Okay, so we've done a couple of different parts. We've broken the vectors into their x and y components. Then you're going to get the total x, total y. All that would remain to do would be to find the angle. And I'm going to let you figure that one out, how you're going to find the angle, and we'll talk about it in class tomorrow. Thank you.